Hi everyone, I hope you're doing well. Welcome to week 5 of our biochemistry weekly reviews. So I'm just going to go ahead and jump right in. A couple of these questions are ones that I also used last week, just the first 2 or 3, just to make sure that we have that same understanding, because last week we worked a little bit ahead. So the first question is explain phi and psi angles of a peptide and using them to describe a Ramachandran plot. So the first thing we're going to do is describe these phi and psi angles. So I know that generally speaking, I have this variable R group here on this amino acid, and then I have nitrogen and another variable R group, excuse me, and so on. And so this is generally speaking, in this case it's a polypeptide, or a dipeptide, excuse me. This would be the general form of a protein. So looking at this central carbon right here, this red line, in other words, the line from the central carbon to the nitrogen, this is where that phi angle is, okay? Phi, all right? And the same thing here, we have this central carbon on the left side, its angle between its central carbon and its N-terminus, that's its phi angle. The psi angle is on the exact other side. So the psi angle is from the central carbon to the C-terminus, okay? And again on this side. So why do we care about these angles? We care about these angles because these angles tell us the conformation of our polypeptide chain. And this conformation is what builds this Ramachandran plot that tells us about our secondary structure. Okay. And I'd like to answer I'd like to spend a little bit more time here discussing the peptide bond, because I think it's one that a lot of students ignore a little bit, but it is pretty important. So just very briefly, and I'm just going to do that as a general bit. So the big part of this peptide bond that makes it a little bit unique is the fact that this nitrogen, if we remember back to organic chemistry, it would be sp2 hybridized, which means that this thing can resonate. And it does to some extent, but not really, simply because that resonance is makes our nitrogen and our oxygen both charged, but it can resonate, and so that makes it to where this bond right here has a partial double bond character, okay, or a partial pi character, all right? And it's about 40% double bond character. What that means for us is that these bonds are rigid, whereas normal single bonds can, rotate around as much as they want. This bond is pretty rigid where it is, and so it's not going to be moving around a lot, okay? So this is important because this is another thing that helps create our secondary structures. Because if every bond in a peptide could rotate, it could create a lot of different structures. But with these bonds being as rigid as they are, the phi and psi angles are the predominant reasons for our secondary structures, and that's why these Ramachandran plots can work. So I'd like to get into number 2 before I actually show an example of a plot. Number 2 asks us what the Ramachandran plot tells us. So it doesn't tell us about which amino acids are present in the protein, but it gives us some indications, and I'd like to get to that a little bit later. The right answer, as I said earlier, is D. It's which secondary structures are present. Exactly, yeah, beat me to it. So the important part so the reason that I say it can give us a hint as to A is because we see some secondary structures are rigid, or when I say rigid, they have these specific angles. So when I look at certain, certain amino acids, for example, proline. Proline is very unique because proline has a fixed phi angle. So that's the N-terminus to central carbon of -60 degrees. So what does that tell me? It tells me that I should never see a proline as a left-handed alpha helix. This will never have proline. Why? Because its phi angle is +60. Okay, so the rigidity of the bonds of some of our amino acids can give us a big indication as to where they could be. Now, it's not always very clear, and as we can see, if we go to the -60 region, we can have a proline in a right-handed alpha helix, or in a collagen helix, or pretty close to a parallel or anti-parallel beta sheet. So it's not always super simple, but it does give us some indication. The other thing I want to point out about Ramachandran plots is we don't know how many helices or how long these helices are, or the sheets are, I should say. We just know that they're there. So we could have an alpha helix that's 5 carbons long, or I'm sorry, not 5 carbons, 5 amino acid residues long, or we could have an alpha helix that's 50. And the Ramachandran plot doesn't really tell us that. It just tells us where, what exists. It doesn't tell us how many, it doesn't tell us how long they are, anything like that. So that's a really important thing to keep in mind, that it's not a perfect system, but it does give us a lot of indication. Okay. Our next question is actually using some of this math with secondary structures. And this is going to be a really big part of your next exam. This, I would say, is probably the second most important part of the exam, with the first being enzyme kinetics. So let's talk about it. Describe the alpha helix, including information about hydrogen bonding and length of helix per number of amino acid. Okay, so very briefly, the alpha helix is a helix. I mean, it looks kind of like that. But more specifically, if this is our N terminus and this is our C terminus, then what we see is, and I'd like to draw this in a little bit more depth, just for the sake of making sure I'm clear. We're going to see, sorry, hang on, I just want to make sure I'm not checking. Okay, yeah, no questions, good. So what we're going to see is, let's see, and I guess I'll draw it this way, and then NH, and then more amino acids, and then over here, I'll draw it there, and so on and so forth. And so what we see is the C terminus of the first few amino acids binds to an N terminus a couple amino acids away, a couple amino acids further. So we're going to be using, we're going to be using this end as carbon number 1. So this is our 1, 2, 3, and so on. And then this is 100, 200, whatever that number is. And so what we see here is the C terminus of our first one binds to the N terminus about 4 away. So this will be N plus 4, or carbon N plus 4, or amino acid residue N plus 4. So if this is residue 3, this would be residue 7. If this is residue 8, this would be residue 12, okay, and so on. All right, then we see, and this trend continues, but this gives us a really important thing. This tells us that, first of all, it's generally speaking, and again, the N terminus is going to be at the bottom, N to C. This tells us that our bonds tend to go like this. NH, carbonyl, NH, and so on and so forth. And this is based on hydrogen bonding. I don't know if I made that clear, but I should have. Excuse me. So because this is based on that hydrogen bonding, what we see here is a general charge. And what I mean by that general charge is the net charge on the N terminus is partially positive, and the net charge on the C terminus is partially negative. In other words, if we were drawing like a polarity arrow, the overall net dipole of this alpha helix is kind of like that, okay? It's not a very strong charge, but it is there, okay? So let's get a couple more numbers in. I mentioned earlier it binds to the N plus 4th residue. So because of that, where would the N terminus of residue 3 bind? 3 minus 4 would give us -1. It can't. And so the first four N termini do not bind because they don't have a C-terminus to bind to beneath them. And we can actually do this on the opposite direction too. The last four, or the four closest to the C-terminus, there's my mouse, last four, carbonyls or C-sides also do not bind because they don't have an amide ahead of them because they're at the very end. Okay, so that's a little bit about the stuff with alpha helices. The next thing we need to talk about is the numbers. So the numbers, okay, yes, perfect. So the numbers for alpha helices, they generally want you to know three numbers. You can get away with two, but I'm going to give all three. So the first is that an alpha helix is 3.6 residues per turn. Turn is also called pitch, and it's basically from, let's see if I can, from this position of the helix to the same position one loop later, okay? And then finally, because we need to get the measurements in, it's also 5.4 angstroms per pitch. So this height over here is 3.6 amino acids, and it's 5.4 angstroms. And just a reminder as to what an angstrom is. An angstrom is a tenth of a nanometer, so I could also write this as 0.54 nanometers per pitch. Okay? Then, and this is a more convenient way if you're just looking for the length, if we take, excuse me, 5.4 angstroms per pitch, sorry, I need a little bit more space, and we divide it by the 3.6 residues per turn or per pitch, residues per pitch, we get this last number, which is 1.5 angstroms per pitch of an alpha helix. I'm sorry, not per pitch of an alpha helix, per amino acid residue, excuse me. So this tells us the approximate height of an amino acid residue in an alpha helix, okay? All right, so now let's use some of this information that we've gotten to talk about, to actually do the math. So number 4, if I have a peptide with 34 amino acids that adopts an alpha helix configuration, how many turns will this helix contain, or how many pitches? Okay, so for this one, I'm going to use 34 amino acid residues, and I know that per every 3.6 residues, we have one turn or one pitch of the amino acid. So then I'm going to say 3.6 amino acid residues per one turn. And the number that oh, and I apologize, I wrote 33, that should be 34. 34 divided by 3.6, the number we get out of that is about 9.44 turns. Okay? And our units cancel, of course. All right? So now letter B, how long is this helix? Well, we know that it's 9.44 turns or 9.44 pitches, and I'm really trying to use those interchangeably because they are interchangeable. We also know that it's 5.4 angstroms per turn. 5.4 angstroms per turn or per pitch. So we can just multiply those two. And we get 51. Okay? So this thing is 51 angstroms long, or 5.1 nanometers long. This is another one of those things that we need to be very comfortable with. They love giving you numbers in angstroms and then giving you an answer in nanometers. Okay, that conversion is very common. All right, the next question. If I have a peptide with 62 amino acids that adopts an alpha helix configuration, how long will the helix be? So in this case, I have 62 residues, and I don't want to have to go through number of turns and then length. I just want to go directly to length. So I'm going to say I know that it's 1.5 angstroms per residue. So I'm just going to multiply them by 1.5. Number I get out of that is 93. So this thing is 93 angstroms or 5.1 nanometers long. And again, we can ask ourselves if this makes sense, because if we look at our previous one, we got 51 angstroms, 4 amino acids, got, I just wrote 51 again, I'm sorry, that should be 9.3. 9.3, or 93 angstroms from 62, so we got almost double the number of amino acids and almost double the length, so that makes sense. Okay. Number 6, and this is kind of the last part of the alpha helix that we should talk about, is using a helical wheel, determine which parts of an alpha helix are polar or nonpolar. So helices are allowed to be, or I shouldn't say allowed to be, because of their conformation, they can be either polar, nonpolar, or amphiphilic, amphipathic, which means they have both polar and nonpolar components. So this one is color-coded because I think it's a little bit easier to see, but you usually won't get one color-coded. And the way that this is set up is it models the actual length of the, it models the actual appearance of this helix in 3D, or I should say from the top. So we start at the very top with number 1, and that's aspartate. But number 2 isn't right next to it. Number 2 is some distance away. It's over here. And then number 3 is down here, and 4 is here. Because we remember that it's 3.6 amino acid residues per turn. This is about 3.6. Okay? So what we see here is this almost clustering of 1 and 5 and 8 and 12 and so on, all near the top. And then 9 and 2 and 13 and 6 are all near one corner, and so on and so forth. But what we get from this, and an indication that we can use to see if we have an alpha helix, is do these kind of clusters work together? And what that means is we see amino acid number 1 is an aspartate, 12 is a lysine, and 5 is a lysine. These are all polar. We like the fact that they're all polar and they're right next to each other. This makes us happy because this is a polar region of our helix. Okay? Over down here, we actually have a very big region between 14 and 2. This is another really large polar region. And I apologize for the not great circling. And then finally, to the left side, we have a non-polar region. So what's an indication that we can use to figure out this, whether something is polar or non-polar? Remembering that we approximately add 4 to get to that same place from question number 3, right? Because the C-terminus and the N-terminus bind 4 residues apart. So if I see a chain and it's something like alanine, lysine, excuse me, aspartate, tyrosine, and then the next amino acid is leucine. Well, I can think to myself, alanine and leucine are going to be in about the same location. And then maybe the next amino acid is glutamate. Okay, so now I'm thinking lysine and glutamate would be in about the same location. So I have to ask myself, does this work with what I know of alpha helices, or will this choose a different secondary conformation to use? I know that my polar stuff is happy, and I know that these guys are both, my non-polar stuff, and I know that my polar are pretty happy too. K and E, they're both polar, that's okay. But then let's say I get, and D and Y we're gonna say are about non-polar. Y is amphiphilic, are about polar. Even though Y is amphiphilic, we're gonna treat them as they're both polar. So then if these next two end up being, say, lysine and isoleucine, well, now these guys don't get along. And so when they overlap, that's not going to be very stable because you're going to have a polar and a non-polar component right next to each other. And it's like mixing oil and water. It doesn't want to happen. And so this, I would assume, probably would not be an alpha helix. Probably not an alpha helix. Does that make sense? That kind of thought process that we use to see, would this work? Can you guys? I just made a random sequence. But in the sequence, the important part is going N+4 from your amino acid to see, do these two get along? Are they both polar or are they both nonpolar? Because that's how our alpha helices like to structure themselves, okay? Good question. All right, so I'm gonna go ahead and shift gears now to the beta sheets. Oh, this one's a good, oh, hang on. Got it. So the 1 to 4 distance is important, exactly. So the reason, so up here in number 3, we talked about how you get that hydrogen bonding between the C terminus of amino acid N and the N terminus of the fourth one later, so of N+4. So them being about 4 apart, like we see with alanine and lysine, and I'm sorry, with leucine and alanine, with lysine and glutamate, with aspartate and glycine, and so on. This gives us an indication that these two will be almost like aspartate and lysine here. They'll be really close to each other. So we want to know, will this be a hydrophilic region or a hydrophobic region, or will they not get along at all? Because if we end up getting, and I'm going to try to match this color scheme here, polar, I don't know if I have an orange, we'll use red, nonpolar, polar, nonpolar, and so on, that's not very stable. And so because of that, this wouldn't, if we were to get that pattern, so in this case, it would be 1, about 5, we'll say this would be 2, and this would be about 6. This wouldn't be very stable because you're putting all the polar stuff in between all the nonpolar stuff. And so what that's causing is that's causing it to be less stable than it would be. Whereas if you had, that was supposed to be blue, I apologize. You had the 2 polar things and then the 2 nonpolar things next to each other, even though they're different in structure. So this is 1 and 5, and this is 2 and 6. Even though they're far away from each other in terms of their primary structure, their secondary structures put them right on top of each other, and that's a lot more stable. Okay? Does that make sense why that distance is important? Okay, terrific. So shifting gears to beta sheets. So beta sheets are a little bit more, I should say, a little bit less fun because they've got 2 different forms. There's parallel beta sheets and anti-parallel beta sheets. So I'd like to talk about them in general, and then I'm going to get to the specific numbers, and I'm going to get to the specific way things happen for each of them, but I just want to talk about beta sheets in general. So beta sheets are formed, generally speaking, they form a kind of zigzag pattern. So this would be one beta sheet, but beta sheets don't come in singles, they come in pairs. So what that means is, and then on this side we get another beta sheet stacked right on top, okay? So, and they don't always have to be zigzagged. A lot of times they're drawn almost like that, like very, very, very narrow differences. The reason we draw them zigzagged is because we use things like line angles that are a little bit easier to see in our drawings. Excuse me. So, because of these beta sheets being the way that they are, the bonding doesn't matter so much between, sheet 1, like within a sheet. It doesn't matter that this thing is polar and then this thing is non-polar or anything like that. It matters that this is polar and this is polar. This is nonpolar, this is nonpolar. So what matters to us is, does the amino acid on sheet 1 line up to the amino acid on sheet 2? Are they both happy with each other? And so on for the rest of it. So because of that, you can get a couple of weird patterns. You can get polar, 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 polar the whole way through, or you could get polar, nonpolar, polar, nonpolar, polar, nonpolar, and so on. So it's a weird difference to see, but this is kind of the interesting thing about beta sheets. So now I've been telling you guys they come in 2 different types, and I'd like to talk a lot more about that, and that's why we have all this space. So, and I'm just going to side by side, parallel, anti-parallel. So there's a lot of differences between them, but there are 4 really significant differences between them. The first is the numbers. So for a parallel beta sheet, it's 0.695 angstroms per two amino acid residues. Okay? Excuse me. Much better. For an antiparallel, it's 0.65 angstroms per two amino acid residues. So how does that look in 3D? Well, maybe a parallel. Oh, and I should explain parallel and antiparallel. I did that last week, but I'd like to talk about it this week because not everyone was here. So if this sheet has N-terminus here, C-terminus here, then on this C-terminus side, maybe you get a bunch of amino acids over this way, and then the sheet starts again. So this is the C-terminus of the second sheet, and this is the N-terminus of the second sheet. So if our N to C are going the same direction, that's a parallel beta sheet. On the other hand, antiparallel, as I'm sure you guys can guess by now, is when they go in opposite directions. So if this is our N, this is our C, well, this is the N-terminus of the bottom and the C-terminus of the bottom sheet. And so they're antiparallel because they go in opposite directions. Okay, so that affects their length because these parallel sheets tend to be a little bit more, how do I word this? A little bit flatter is, I guess, how I want to say this. So rather than being very, very, very jagged, they tend to be a little bit flatter. And that's why they're a little bit longer. Okay, I don't know exactly why that is, to be honest with you. It's just one of those qualities. So that's the first difference. The second difference is in the bonding. So I'm trying to think of the easiest way to draw this without drawing an entire structure. So when we have something like this, and I'm just going to draw N to C, and then this is going to keep going and loop around to here. And then once again, our N to C going this way, N to C. What happens with our hydrogen bonding is we get, if you want to think of it as bent hydrogen bonds, we can. So this thing is going to have whatever group coming off of it. Let's say this is the hydrogen, and this will be the carbonyl. Your hydrogen bonds, I should have drawn them more like that because that's more appropriate. Your hydrogen bonds end up being bent. Yeah, okay. On the other hand, with our antiparallel, and I'm just going to assume they go right away, but you can have a, just realized I drew that in bound as well. I need a gap. There we go. So I'm drawing them as if the region between the two sheets is very, very small. You can have a large region or a narrow region. It doesn't matter too much. Okay. I think that gives me enough space. Okay. These have very straight hydrogen bonds. So these hydrogen bonds are almost like lined up perfectly. And a part of that is just based on where they are relative to each other. Because the parallel sheets are lined up perfectly, what you see is N to C, skip the carbon, but that's okay. Let's draw it this way, that's fine. And then you get the exact same thing on this side. And so what ends up happening is the hydrogen here has to bind to this oxygen, and the carbon here has to bind to the nitrogen this way. And so they're not, since they're lined up perfectly, the N-terminus and C-terminus being slightly off of each other causes these bent hydrogen bonds. Whereas over here in the antiparallel side, if we treat it as like one amino acid in this section and then one amino acid in this section and so on, well, this is going to have N-terminus, C-terminus. This is going to have N-terminus, C-terminus. This one's going to be flipped. So you're going to have the N-terminus on this side, and I guess actually other way, shouldn't I? And then C-terminus on this side. And so the hydrogen bonding can happen straight up and down because of it. Does that make sense? I don't know if it does. It's a little bit weird to kind of wrap our head around. So please ask questions if you're confused. Okay, awesome. So that's our second difference, is the hydrogen bond being either bent or straight. Okay. The next is our side chains, and our side chains do have an actual impact. So what we see with our parallel beta sheets is hydrophobic side chains can appear on both sides. So, and for the sake of simplicity, I'm just going to label them N for nonpolar, like we've been doing. So you can have nonpolar here, nonpolar here, all over. Whereas with antiparallel, your hydrophobic side chains tend to be concentrated toward one side. Okay. Once again, I'm not really sure exactly why that is. It's just a general trend that we see. And the final difference is in terms of stability. Antiparallel are more favorable. And the parallel are less favorable. And this comes partly because antiparallel have those hydrogen bonds right on top of each other. It lets them be a little bit closer, so they're a bit stronger because of that. Okay, so those are the four big differences between parallel and antiparallel. Between parallel and antiparallel beta sheets: the length, the stability, the bent or straight hydrogen bonding, and then the location of the hydrophobic side chains. Okay. So now we get the fun part. You're going to be getting a lot of math that's not very fun as we start going through this unit. So the very first question that I am giving you guys for this is hard. So given a protein with the various length, that should not be typo, that forms an antiparallel beta sheet with half its amino acids and alpha helices with the rest, determine how long this protein is in angstroms. So before I do this math, I want to start off by saying this is not a very great example. And the reason for that is when you have beta sheets, and I'm just going to use what I have in number 7, you have these kinds of regions. These in between secondary structures, you need to have these little regions for them to move around, for it to kind of get ready to form a structure later on. And so this is a pretty rare occurrence that every single amino acid residue is going to be in these secondary structures. But this is just for the sake of simplicity. In reality, it might be that 20 of these amino acids are kind of just not in a secondary structure, and then the rest of them are going to do something. But I wanted to keep it a little bit simpler, just because, well, I didn't want to do the math, to be honest. So 234, the first thing we're going to do is just divide it by 2. So now I know that I'm dealing with 117 alpha helix residues and a number of beta sheet residues. So I'm going to go ahead and do that math. So 117 residues. I know that per residue of an alpha helix, it's 1.5 angstroms. 1.5 angstroms per residue. Okay, so I'm going to go ahead and just multiply them across. 117 times 1.5, and I'm going to get 175.5 angstroms. Okay. The second, this one's a little bit weirder. So remembering that this is the antiparallel, and I'm just going to go ahead and slide over here to make sure. Antiparallel is 0.65 angstroms per, and I didn't copy this over, per 2 amino acid residues. Excuse me. So I'm going to go ahead and just write that down. 0.65 angstroms per 2 amino acid residues. And the reason that it's 2, I hope makes sense that we're talking about 2 sheets kind of stacked on top of each other. So it's 0.65 per residue, but because there's two residues wide, if we want to think of it like that, that's why we get, so I guess, yeah, using this up here, it's 0.65 per single residue, but there's 2 stacked on top of each other, and that's why we get that, that number, okay? Regardless, the actual math works out, excuse me, to give us about 38.0 angstroms. And then when we add that to that 175.5 we got before, the overall length of this protein is 213.5 angstroms. Okay. Or, and I think this is a little bit easier to see it, 221.3 nanometers. It's tiny, but yeah. Does anyone have any questions about the kinds of calculations asked to do with parallel and anti-parallel beta sheets, with alpha helices, any of the math? I'm gonna give you all 1 second, and then I'm gonna go ahead and move on. So I kind of spoiled number 9 because I didn't realize, I knew I had it on, I didn't realize it was so close. I was hoping it would be a little bit later. So I'm just gonna very briefly mention it again. Proline's fixed pi angle is negative 60 degrees, okay? Because of that, if we want to think of negative 60 as being probably about here, it can appear in right-handed helices, it can appear in beta sheets, kind of, but it's not great. It could never appear in left-handed alpha helices, and that's why this answer is B, okay? Does that make sense to us? I just want to make sure that I explained it well above, or I can re-explain it. Actually, before we move on, why is Proline's phi angle fixed? Let's ask that. Yeah, it's a cyclic structure. So just so that I'm complete, here is the image of proline that I want to show you guys. Oh God, okay, we're just gonna ignore it. Never mind. So yeah, proline's got, this is its central carbon, and then this is its bond to the N-terminus. It's very rigid here because what we're dealing with is this cyclic structure. And so it's got this forced bond of about negative 60. I don't know exactly if that matches with what a pentagon would normally have, but in this case it is. So it can't change it around. Whereas something like, glycine, just a regular amino acid with just an NH2 here and hydrogen, hydrogen there. This bond is free to rotate pretty freely, and so it can hit a lot of different angles. Okay. All right, so describe a beta turn. And for this, I think it's not a really easy topic, but it is a fairly simple. So a beta turn is called a beta turn because it's very similar to beta sheets in the sense that, I should say it's very similar to anti-parallel beta sheets in the sense that they kind of loop around, form straight hydrogen bonds, and then just keep going back. However, this is a like 3, maybe 4, if you want to think of it as 4, amino acid turn. So I just want to start just on the type 1 is what I'm going to be drawing on, because there are 2 types, but I'll get to that in a little bit. So what we see here is our first central carbon, our first C terminus, and then to the next amino acid, to the next amino acid, and then on the other side, so the N terminus of the 4th amino acid away. So this is 1 to 4, so it's a difference of 3. We have this hydrogen bond. If you notice with the type 2, it's the exact same thing except for this part right here. Okay? Why? Does anyone know actually, before I just give the answer away? It's not a particularly difficult thing. It's just kind of the how do I word this? Just the orientation of the peptide bond, I guess, is how I'll describe it. So again, coming back to the idea, these peptide bonds are rigid, so they can't move around. Because of that, it creates this and this as different because of the rigidity of that peptide bond. Okay. So that rigidity also kind of has that ripple effect of causing different bond angles, and that's what I want to point out here. So the phi angle of +1, which is I + 1, which is basically 2. I should say R2. So it's referring to this amino acid with the phi I + 1, and this amino acid with the I phi + 2. Okay. What we see here is, and the reason that I want to point this out is this tells me proline would be very happy. Proline is very, very, very prevalent in these beta turns because the phi angle is -60. More appropriately, I should say the phi angle, they're very prevalent in this position because of that phi angle in both types of beta turn. Okay. Glycine is also prevalent. I believe it's because it has the freedom to rotate anywhere it needs to, and not all the amino acids have quite as much freedom as glycine would. Okay. The way that I think about beta turns, and this is something I haven't had a chance to include yet, is beta turns are almost like a 3-residue, 0-pitch helix. Like it's literally a helix because it just rotates around, except not quite. I personally also think of it as a as an antiparallel sheet that's like one long, but because both are acceptable. Okay. So with that, we're getting pretty near the end of this chapter. So I have a couple of application problems, and then I have a couple of kind of working ahead into the enzyme kinetics, which I believe is chapter 13. And then that's pretty much the end. So we're just gonna, I think, finish this pretty quickly. So number 11, consider the, I should mention, the reason we're finishing this quickly is because there are a lot more super secondary structures. There's things like coiled pins, beta hairpins, the beta alpha, beta motif, helix, turn helix, all these things that I don't know how much depth you need on all of them because it's very professor dependent. Some professors want you to understand them well. Some professors want you to know their name and what they look like. And so I don't want to cover that in a ton of depth and then, waste some of your time depending on your professor. And I don't want to just talk about them very, very briefly and act like that's all you need to know because you might need to know more depending on who you have. And so I wanted to leave that part and just kind of mention it here as just so study this as much as you need to without getting into the depth on it to make sure I wasn't giving false information. Okay. Now let's jump into number 11. So considering this oligopeptide, actually I don't know, nope, I can't zoom in anymore, can I? I can, okay. What secondary structures would you predict for this peptide? So we're gonna do exactly what we did before, and I'm just gonna label polar, non-polar for each of these. So methionine, basically non-polar. Glutamate, once again, polar, and proline, non-polar. Okay. So what I'm going to do first is just see, is there a trend of them kind of like alternating polar, non-polar, polar, non-polar? Because that could tell me that I have a data sheet of some kind. So kind of, with the exception of glycine, it's non-polar, polar, non-polar, polar, non-polar, polar, and so on. So beta conformation is possible for this one. Okay. The next thing I'm looking at is, let's go n plus 4. So alanine plus 4. And actually, I'm going to go ahead and write this out separately so that I have the room to kind of to draw around without kind of confusing everyone, because there's going to be a lot of things. So A, and I'm going to go 1, 2, 3, 4. So I'm going to go to leucine. Well, yeah, those would be happy. They're both nonpolar. E, 1, 2, 3, 4 to lysine. Okay, they're both nonpolar, or they're both polar. That could be good too. Phenylalanine to methionine. It could be. Glycine to glutamate. Not really. And then leucine to proline. Okay, yeah, that could work. So an alpha helix could also be possible. Not perfectly, but it could work. An collagen helix is not really one we talk about often. It's not one that I mentioned because it's a very minor secondary structure. And so I'm actually going to turn it over to the two of you. What do you think? Which one do you think it might be? I hear some. Not sure. Beta structure. Okay. So it's a very good guess. And I say you're actually correct. It is a beta conformation. If I can ever find my mouse, I would love to circle that for you. Oh, there it is. Okay, beta conformation. And the reason behind that is seeing this non-polar polar pattern pretty much working is very, very good. Whereas again, when we look at our alpha helix, really what we should be looking at is that helical map we talked about. And what I'm thinking to myself with a helical map is, I can't see through all the drawing I did, but I think it would be glutamate and lysine was good. It was glycine and glutamate. So that G ... E, those guys are going to be right on top of each other. That's not very stable, all right? Whereas with this oligopeptide, with a beta conformation, the reason we like the non-polar polar thing is because these guys can, I guess I should have drawn those in different colors. Let me riddle. These guys can interact a little bit with their R groups. These guys can interact a bit with their R groups. So what we see here is non-polar, polar, non-polar, polar, and so on. That's really, really good. It's not necessary for a beta sheet, however. We just like seeing it. Really like seeing it, to be honest. And so that's kind of what sways me toward a beta sheet, is that pattern isn't 100% necessary, but having it really helps, okay? Does that make sense? Okay, terrific. So this is another question from that I put from last week's, just because I think it's really important to keep in mind, especially as we're talking once again about, or I guess because the end of chapter 6 talks a lot of energy, so I want to make sure that I mention it because it is a pretty important thing. So what this question is asking in a ton of words is, which of these, non-covalently linked chains means secondary structure, tertiary structure, quaternary structure. In other words, which of these does not denature proteins? What do you guys think? So just a reminder, chaetropes would be something like a guanidine. I can't pronounce that. I apologize. GuHCl, guanidinium chloride. I think I said that right. It would be stuff like urea, stuff like that. Okay. So, not seeing anything in the chat. That's all right. I'll just go ahead and give it. Oh, hang on. Yeah, it's definitely not A. Extreme pHs are very, very good at denaturing. It's also not, or it's also and these chaetropes are very, very strong chemical. I think they're called the chemical detergents or something. They break up bonds, and so A and C are definitely correct. So actually, I included 2 wrong answers here intentionally. High salt and reducing agents. So I want to talk about those separately. So high salt, this is for salting in, salting out stuff, right? Specifically, this is salting out. Does this affect the secondary structure? Or I'm sorry, does this affect secondary, tertiary, quaternary structure? Ooh. Okay, so no, I wasn't seeing it. I think it might be a little bit. So this one is actually technically correct. Reducing agents. So reducing agents are used in protein sequencing, and that's where a lot of this comes from, but this topic was repeated. So I want to actually, I think it was last week. So I want to turn back to week 4. So protein sequencing, the first step is to separate non-covalently linked chains. The second step is to break and block disulfide bonds. And actually, I do believe high salt can do this, but I didn't think it did. So I'm not certain about that. That's what I want to check on in a little bit. But the important thing is reducing agents for that step of in protein sequencing, they don't break non-covalently linked chains. they break disulfide bonds. So break disulfide bonds. And as we discussed, I believe it was last week, disulfide bonds, as much as I hate saying this, count as primary structure. It's not something that I'm very happy saying because I don't think it makes a ton of sense, but it is the truth. So because of that, reducing agents are the formal right answer to this question. Reducing agents are the right answer to this question because they break covalently linked chains, even though this is a part of protein sequencing. It's just not the part we're looking for. And very briefly, I just remembered this high salt does not correspond to salting in and salting out. It's using salts like ammonium sulfate that are very, very, very strong salts to disrupt these chains. And so this is actually a wrong answer to this question because it can be used to separate these chains. So it uses stuff like ammonium sulfate. Okay, all right. 13, this is a new one. Which of the following best describes the melting temperature of a protein? So, and I think you guys have probably all seen that kind of graph that looks like that. So this is basically, I think it's energy is how it's defined. But basically what we see here is, it's folded protein and unfolded protein and temperature. So TM, or the melting temperature, is right here, okay? So based on that, which do you think is the right answer? A, B, C, or D? Or rather, which of these are definitely wrong if you're not sure? C. So C so again with this one, I included two right answers. This one was a lot more intentional. So C and D are both correct here. So, and I want to talk about why A and B aren't, and then talk about C and D a little bit more. So the temperature at which 100% of protein is denatured, this one's fairly simple. We deal with 50% here, okay? And the reason is, when you're dealing with something like 100%, a lot of this is in equilibrium. And so to get 100%, you're going to need like a really, really, really high temperature. Like even down here, right here, that's probably not 100%. That's close to like 99, 98%, but it's not quite zero. And so to get to zero, you're probably going to have to use a pretty unreasonably high temperature. And so just for that reason, we don't really like using 100% in things like biochemistry, okay? The temperature at which quaternary structures are broken, but before secondary or tertiary structures are affected, that one's just wrong because melting is about unfolding the protein, and it's about bringing it back down pretty much to its covalently linked chains, okay? And that's what I want to talk about here. Denatured and unfolded kind of mean the same thing. It means the breaking of the non-covalently linked chains. Very weird for a lot of students. It's not something, and it's something that I personally get annoyed by all the time too. I don't like the idea of denatured being the same as unfolded. In my head, denaturing a protein is like breaking it apart, because that's how we've been learning it all this time. And unfolding is something a lot more simple. And so to me, it doesn't add up very easily, and that's why I wanted to include this question. But the truth is, they're the same thing because both of them are saying breaking of secondary, tertiary, and quaternary structures. Okay? Are we okay with that? I'm glad you guys are, because I'm not. Okay. So chaperones. This is a really interesting section. So chaperone proteins help other proteins fold. And the reason that we sometimes need chaperones is when you've got a folded protein and an unfolded protein that are similar in energy, like just going to delta G. So if the delta G of folding, if it is spontaneous, but it's a low spontaneous number, so it's something like -1 joule per mole or something, so a tiny number, that's a very, very slow protein folding. But I only have proteins in my body that are like, I only have my protein enzymes, I should say, when I need them. Unless they're always on, in which case I still need them all the time. So this doesn't work. My body is not happy with it being that slow. So what is it going to do? It's going to use these chaperones to speed that up, okay? So, and that's kind of something we're going to talk about with enzymes in a little bit as well. It's to speed up a spontaneous reaction. So this is just one of those things. I don't know how well you need to memorize this. Again, it's probably a very professor-dependent question. But the important thing, but one thing to recognize is that only 3 of these are chaperones, despite them 60, 70, 80, 90, like that's pretty good to me. 80 is not a chaperone protein. 60 is, 70 is, and 90 is. Okay? One other thing to mention here, just very briefly, is that HSP stands for heat shock protein. Heat shock protein. Sorry about that. I dropped my headphones. So these heat shock proteins, the reason they're called that is because they're upregulated, or they're more on when they're exposed to heat. So having heat activates these guys a lot more, and that speeds up protein folding a lot more. Okay. And they work by binding to exposed hydrophobic regions. I don't want to get too deep into the weeds. Okay. So enzymes are the second major topic of this unit. So enzymes, and this is just very, very brief characteristics of enzymes, they catalyze thermodynamically favorable reactions. So just like we talked about with heat shock proteins, they don't make reactions happen that don't want to happen. They just speed up the ones that will happen. And if we look back to, I believe this would have been drawn for you guys in Gen Chem 2, they lower the activation energy. That's the big job of enzymes, okay? They act on specific substrates and catalyze specific reactions, and they get regulated. So I want to explain this part a little bit before we get into the types of enzymes. So how do they catalyze thermodynamically favorable reactions? They stabilize the activation state. How do they do that? Charge. And that's kind of the short answer. So if I have this protein right here, and it's very, 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 very negative, and I have an unstable transition state that goes positive. Okay, so this transition state that goes positive, it's really unstable when it's positive. So by putting it right here in this protein, that stabilizes the transition state and makes it a lot easier for this reaction to happen. Okay, the reason they have to act on specific substrates and catalyze specific reactions, this negative region might be something like that only fits this specific shaping. This negative region could be, really small and only fit certain parts in, things like that. Or it could be a million other things. There's a lot of ways that for enzyme specificity. And lastly, getting regulated. pH is a really great way to regulate this, because if this is negative and I lower the pH to maybe like 4, well, a lot of this might get protonated. And in that case, that's decreasing the efficiency of my enzyme without denaturing it, because it can still get denatured maybe at pH 1 or lower, but at a pH of 4, maybe this is just it getting regulated and kind of turned off, if that makes sense. Temperature can also regulate by just disrupting the enzyme structure, but that's denaturing. You can use inhibitors, which we're going to talk about very much in the next section, which I'm very much looking forward to, things like that. Okay, so let's talk about class of enzyme. So there are 6 general classes of enzyme that you guys are going to need to memorize. I believe some professors include a 7th. That's a professor-specific question. These are the big 6 that everyone has to memorize, though. Okay, so oxidoreductases do oxidation or reduction. Transferases transfer apart. Hydrolases cleave with water. Lyases cleave without water. Isomerases change the attachment, or change the way something is attached. And ligases put things together, and that's a weird one. Okay, so I'd like to talk about these in a little bit more depth, and then we're gonna go back and actually answer this question. So I hope we remember oxidation and reduction from Gen Chem and maybe a little bit from OChem, depending on what you guys learned. It's the transfer of electrons. Transfer of electrons, change in oxidation state, all that stuff. Okay, so this one is fairly simple. It could be something like AH plus B goes to HB plus A minus or something like that. The oxidation states of B and A are both changing because of the transfer of a proton as well in this case. Okay. Transferases. So transferases transfer a substituent. So the way this would look in real life without using these building blocks, sorry to say I've lost my mouse. There it is. So over to the left here, so if I have A and it's attached to this thing X, and I add B to it, and this should be in equilibrium, let me make that better. There we go. The other side would be now B is attached to X, and I also have A. Okay? So these don't really affect charge, they just move things around. Okay? Hydrolases, well, we know a reaction that can be sped up by a hydrolase. Or rather, I should say, we know the reverse reaction that can be sped up by a hydrolase. Okay? It's the formation of a peptide bond, right? I guess over to the right, I'm just trying to find space here, really. Remember that a peptide bond is central carbon, R group, all that stuff, and then you've got this NH2, and you react it with this, and what happens is when this attacks, this is eventually going to fall off along with one of these hydrogens, and H2O leaves. Well, that's, excuse me, that's a classic hydrolase, okay? And that's why over here, actually, we see a common example is the peptidase. The formation of a peptide bond is a hydrolysis that's sped up by a hydrolase, okay? Lyases, these are called synthases, and they put things together. And I believe I misspoke and called these cleavage reactions. It's not entirely accurate. So lyases is quite literally A plus B goes to AB. Fairly simple. Isomerases move things around. So instead of AX with X attached to the right side, maybe we'll get AX attached to the left side or to the bottom or wherever else. Obviously, in real life, it would be something a lot more complex with maybe an R group here that gets moved to here, but that's just a general example. Okay, and ligases. Ligases are weird because a lot of you guys are going to think, well, isn't it just a lyase? And you're technically right, but ligases use energy. I should say energy they don't have really. So if we notice, we have XTP, and X is just the RNA nucleotides, so adenine, guanine, uridine, and cytosine. So remember that when we put those with ATP, or with, ATP is actually an example, let's talk about that. We get adenosine triphosphate and so on. So we use the energy of XTP cleavage in order to synthesize something. So these are very different from lyases, or these are slightly different because lyases synthases don't use like an external energy source. Ligases do. Okay, so let's talk about this this question. What kind of reaction do you guys think this is, or what kind of enzyme, if you just want to jump to the answer? Anyone? Any ideas? Okay. So what we see here is a change in oxidation state from -1 and 0 to 0 and -1. So to me, that tells me electrons were transferred. Electrons being transferred tells me this is an oxidoreductase, or I should say an oxidoreductase could speed up this reaction. The other thing I want to once again emphasize is it's not just an oxidoreductase, it's got to be a very specific one. So that's why these classes are also different. We can't just throw in any oxidoreductase and assume it'll work. We have to throw in AB oxidoreductase, okay? Then the last one is kind of another, this is what you guys are about to start. This is enzyme kinetics, okay? And this is, in my opinion, the best unit. It's a ton of fun, but important things to keep in mind here are this reaction is kind of the building block of enzyme kinetics, so I really want to talk about it in a bit more depth. So just explaining this figure with regard to the elementary reactions, remembering again, all the way back to Gen Chem, the elementary reaction is an individual step. So I'm going to change color so that we can see the individual steps. This is one step. Your E and S going to ES, and I'm going to explain this figure in a lot more depth in a moment. Your second step is going to be ES going to P plus E. So what are all of these words, or all of these letters? So E generally means your enzyme. Y is the substrate of the enzyme. ES is not just enzyme plus substrate, it's your enzyme substrate complex. So what that means is your reaction is not just enzyme makes substrate into product, it's that your enzyme and substrate have to bind first, and then they can form a product, okay? And that's what we see here with P. P is product, and once again, we're given a free enzyme. Okay? So again, remembering back to Gen Chem, every elementary step has its own rate constant, and that's what these Ks are. Because this is a reversible reaction, this first red one is, we have actually a we have a K1 and a K negative one. So what that means is E plus S to ES follows K1, ES to E plus X follows K negative 1, okay? So just based on this kind of step alone, we can tell if the rate constant K1 is greater than the rate constant K negative 1, an enzyme substrate complex will form. Are we okay with that? Yes, okay, great. So now, the last part of this is the blue part. So once you have your enzyme substrate complex, it can do one of two things. Like we talked about, with K negative 1, it can go back to enzyme and substrate. Or with K2, it can form a product. Okay, so this, sorry, I just want a little bit more space here. So this kind of choice, I say, that it has is also dependent on the rate constant. If K2 is greater than K negative 1, product will form, I guess, relatively quickly is how I want to describe it. And there are more specific terms that I'd like to talk about next week, but I don't want to jump ahead too far. Okay. On the other hand, if K negative 1 is greater than K2, then what we'll see is more free enzyme plus substrate forming than product. So product will form a lot slower. It will form slower. So this reaction is also where, or I should say, this kind of figure of the reaction steps is the entire basis of this next unit. It's where we introduce the terms, the equilibria terms. It's where we introduce a lot of formulas that are about to start come from this equation. And it's where we also talk about inhibitors a lot more. So those are the really big parts of this are the math of this formula and inhibitors, and they're all based on this formula. So if you have any questions, I very strongly encourage you to ask now, because you want to get this part down before the next section, okay? What do you guys think? Okay, terrific. Well, then that's all I had. Unless you have any other questions, I'm going to go ahead and stop the recording.